Well, first of all, let's go over what we have learned. Okay, we know that the geometric series, when it's convergent, when it's divergent. Okay, so this is a formula. Okay, okay, and that is going to be a r to the capital N 1 minus r if absolute r is less than 1. Otherwise, divergent if absolute r is greater than or equal to 1. Okay, that's what we know. We also know that in order to check whether it's convergent from the definition, right? then this by definition, right? So this is going to be the limit of the partial sum. So if we can find if we can find expression, simple expression for the partial sum, then you probably can figure it out. Okay, that's the definition. Okay, so you can use definition to show that whether this is this series is convergent or divergent, even if you find the value. Okay, and the next one, I think I remember as this is the first one, right? We learned second, third. If this is a convergent, then the limit of n approaches infinity is going to be 0. So you can use that to prove. You can only use that to prove the series is divergent. Okay, because in case the limit is not going to be 0, then, or maybe that doesn't exist, then you can show that. Then you can say that this series is divergent. Okay. So this is about what we learned. Okay, and the question is, how do we check some other series, whether it's convergent or whether it's divergent? Okay, and we can also use a comparison test to check the convergence. Okay, so this is also important skill, important method. We can use it. Okay, so for example, let me check whether we already learned this or not. No, we haven't learned this yet. We will do this a little bit later. Okay. So the next question is, so here's the example, right? I'm going to study this series today. It's from capital N, okay? So N is to power P, okay? P is greater than 0. Otherwise, this is if P is 0 or it's obvious or negative, then this clearly this is divergent, okay? So note that, okay, the limit of n approaches infinity, the nth term is going to be 0. So the question is whether this series is convergent. I cannot use the third one to prove it's convergent because this is by logic, this is from left to the right. So if it's convergent, then the nth term, the limit of the nth term is 0. But conversely, you cannot say it's convergent, right? The series is convergent. Now, how do we check whether it's convergent or divergent? Okay, so here's an idea. Okay, I'm going to consider a function. Okay, so we have so here's a function. Okay, this is an idea. I let fx to be x to the power x. Okay. Then for x between between n plus 1, let's say k greater than or equal to k, then you will see that, okay, then you see that x to the power is less than or equal to k plus 1 to the power p and greater than or equal to, right? So then you put into the denominator, and then you will be in the opposite direction. Okay, so that's what we have here for x between k and k plus 1. So I can integrate. I put the integral, okay, from k to the k plus 1. So this dx, because there's upper bound here. So actually still you have this inequality. You know why? Because the size of the interval is 1. So if the function has the upper bound, then the upper bound times the difference of a k plus 1 and the k, then it's 1. So you have this. Then you add all together, okay? You add them all together. Similarly, you can have a k minus 1 to the power k xp, right? This is k minus 1 to the power p, and this is a k to the power p, okay? Then keep it going, and the last one will be capital N, okay, to the n plus 1. And this will be n to the power p and greater than n plus 1 to the power. Okay, now if I add them together, what do you get? If I add them together, this side, so I have to introduce a notation xk to be n from capital N to the k, right? And 1 over n to the power p. Okay, this is a partial sum. So when I add them together, all together, right? And this will be the integral from capital N to k plus 1. Okay. This side will be, I think, from capital N to the k. This is just sk. Okay. The other side, because there is the first term is missing, sx is sk plus 1, but I have to subtract this term. Okay. So you have this inequality. Okay, so this you have this inequality. Now, then you let the k to infinity, right? Let the k go to infinity. What you get is let k approaching infinity. Okay. First of all, the limit. This one is a finite, okay, or in positive infinity. You know why? Because this sk is an increasing function sequence, so it's going up, right? Every time you add the positive terms. So both sides above inequality gives you you will get 1 over m to the power p and less than or equal to n to the infinity, and here's xo, okay, right? It's less than or equal to, okay. I forgot minus capital N to the power p. Okay, so that's there's a small term here difference. Otherwise, they're both sides equal. Yeah. Okay. So now you will see that the series convergent if only if the integral is convergent. So you can conclude the following fact. Yeah, you can conclude that conclusion. Okay. This is a finite if and only if this integral is finite. Okay, because this integral is a finite or it's infinity, right? Now, when this integral is finite, we remember we did that if and only p is greater than 1. Okay, right? So this is, I'm not going to go through this again, when this improper integral, yeah, has a finite limit. Okay, so this is called the P-series test. If you have a P-series, we call it P-series. When the P-series is convergent, only if and only if P is greater than or equal to 1. Okay, so we get the following so-called the P-series test. Okay, so this is a finite if and only if P is greater than 1. Okay, and in general, okay, I'm going to state the theme. In general, you have, okay, so here's a general theme. Best use the same idea. Okay, so here's a function. We assume that if f of x, okay, continues and decreasing, okay, on the interval from n to infinity, okay, then for this sequence, okay, the following identity holds. Okay, so this is from capital N to infinity. Sorry, this is harder. Yeah. So we have minus is the last term. It's going to be less than or equal to the integral from n to infinity of for fx dx less than. Okay. Okay. So you can tell that when it's convergent and when it's divergent. Okay. It approaches. Oh, sorry. This is should be positive. Yeah, positive, decreasing. Yeah, we're talking positive functions. Okay, there's three conditions here: positive, decreasing, continuous. So this is kind of function. Here's the n. Right. All right. So if here's n, then this is a value of n. Okay, n is going to be equal to f of n. That's a picture. Okay. Okay. So not this is a very important theorem also, and you can use the theorem. Actually, you can estimate the value of the series. Okay. You can estimate the value of series. Okay. Let's go back to let's go back to this. Okay. This is a start from 1. Okay. 1 over np, and I know it's convergent when p is greater than 1. Okay, so remember, this is this series minus the first term is less than or equal to the integral from 1 to infinity, right? And so I can estimate the value. Okay, I assume that p is greater than 1. Okay, so remember, this is going to be, I think it's going to be, the value is going to be, check. I think it's p1 over p minus 1. Yes. Okay, so the value is when p is greater than 1. So from here, you can tell that using this identity, so you get it's greater than 1 over p minus 1. It's less than, using this identity, it's less than 1 over p minus 1 plus 1. So You cannot get the exact value of this series, but you can estimate. Okay, so it's good to estimate. Actually, the difference is the lower bound, upper bound. The difference is what? Okay, the difference is what? This is a very important. Yeah, this is a very important result. Okay. So now let's take a look at the following example. Okay. Right. So we're not sure this is a convergent or divergent, but what we know is we know that one of it. Okay, we know this is divergent. This is called the Harmonica series. Okay. We also know that when this power is 1 plus a small positive number, this is convergent, right? Why? Because P is 1 plus epsilon. Yeah. Because P equals 1 plus epsilon greater than 1. Okay. But this n, okay, this n over natural log of n, this number, okay, grows smaller than n plus 1 epsilon greater than n. So it's between that, slightly larger than n in some sense, okay, for larger n, okay. That's I just say this is not always true when n equals 1, for example, and n equals 2. When n equals 2, natural log of 2 is not, that's for large n, I'm saying, for large n. Okay. So the question is whether this series is convergent. It's not easy to check, okay? It's not easy to check, okay? I want to make sure this go to 0 very fast. So if we put it in the denominator, it's greater than, it's less than 1 over n, okay? But still, if this is too close to 1 over n, then it's divergent. If it's very close to this term, it will be convergent, right, the series, right? So we don't know. So what we know is this will be the value of the function. The function is x, okay, right? And then n, 1 over n natural log of n is going to be f of n. So we can use the above theorem to check its convergent or divergent. So we have to check the following condition. If f of x is greater than 0, that's clear. For x greater than or equal to, okay? Okay, right? Second, is f of x decreasing? The answer is yes. Okay, decreasing, positive and continuous, right? Of course. So now I'm going to check this integral. Okay, whether this integral is convergent or divergent. All right, so the n, right? I want to use a substitution. I let u to be natural log of x. So du is going to be 1 over x dx, right? Okay, so this is going to be integral, natural log of 2 and positive infinity. And here it's going to be u and du, okay? So that is going to be actually the natural log of u, and try to evaluate the two endpoints. Now, yeah. I skip a step by taking limit here. But this is clearly is going to be infinity, right? Because natural log of infinity is infinity. Okay. So it's divergent. So that means it's an integral. Yeah, you know, we have this one, right? F of x dx, and this is a sigma, right? And greater than or equal to, and minus 2 natural log 2. But this is a infinity, right? So that's why that's force the one on the right hand side, that forces the one on the right hand side that being infinity. Okay, so conclusion is the value is infinity. Yeah. Okay. So it's divergent. So that means n times natural log n goes really very close to as 1 over n. Okay. I know decrease. Yeah, 1 over n times natural log n decreases almost as fast as 1 over n. And so integral test is pretty useful method. So let's take a look at the next problem. So the next problem is this one. Okay, n start from 1. Here n squared plus 1 and okay. Now, how to check whether this series is convergent or divergent? Okay, there are a couple ways to do. Okay, there are a couple ways to do. Right. The method we're going to use here, that's what we learned today. Right, the integral test. Okay, so I consider this n, right, is a value function. Okay, is a value of this function. Okay, so yeah, you let fx to be that, then 1 over n squared plus 1 equals f of n. What we have to do, yeah, so this f of x positive decreasing. Okay, that's all we need. Okay, and so you can use the integral test to check whether it's convergent or not, to check the convergence. And not only that, you can even estimate. Okay, so we conclude that sigma n starts from 1 and minus the first term, which is 1 over 2, less than or equal to the integral from 1 to infinity, and less than or equal to. Okay, so can we evaluate this integral? Answer is yes. Okay, so the integral, because we can find the antiderivative of this function. Okay, more precisely, you should put it as a limit. Okay, sometimes I skip that step. Okay, so the antiderivative will be arctangent x evaluated at the two end point. So you will get arctangent b minus arctangent 1. Arctangent 1 is pi over 4. Right, this is a pi over 4 because tangent pi over 4 is 1, right? And this one approaches pi over 2. Okay, so pi over 2 minus pi over 4 is still called pi over 4. Great. So it's convergent. Now, once it's convergent, then you can say that this this is going to be n squared plus 1 minus 1/2 less than pi over 4 less than this. Okay, so in other words, you can rewrite this using this. You can, okay, this is greater than pi over 4 using the integral on the right, inequality on the right hand side, and this is less than or equal to 1/2 plus pi over 4. Okay, so you get an estimate. Not only you prove this convergent, you can also get an estimate. Okay, this is the power of an integral test. But if you just want to know whether it's convergent, here's another way to do. Okay, we probably can study, spend more time to so-called comparison. Okay, we know that this is n, right? N squared plus 1. And I know this is less than or equal to less than or equal to 1 over n squared, right? So it's not bigger than that. Then the partial sum and n starts 1 to k. Right? I want to make sure this is a convergent to a finite number, right? And then you will see that the right hand side is just as a p series, right? So this is another term, but we know this is a k is arbitrary, so we know this is less than the limit. Okay, this is a finite. So that means the partial sum has an upper bound. In other words, sk is less than or equal to n equals from 1 to 1 over n squared. This is a finite number. This is by the p series test. We already know that, right? And I can even give you the upper bound for you. I think this is do we remember, right? We already did this. Let's go back. No. Yeah, it's here, right? So when p equals 2, it's going to be 1 over n, so actually less than 2. Yeah, so I can even tell you, yeah, so sk has an upper bound. Right, has an upper bound. It's less than 2. Right. However, as a sequence, sk has an upper limit. It's increasing, right? Because every time you add the positive terms. So therefore, this limit, okay, which is going to be the series of, okay, and this limit exists, and less than or equal to, okay? Great, so this is another way to prove this series is a convergent and has upper bound too. Okay. So you can avoid using the integral test, but actually you still use the integral test. You know why? Because indirectly, because you already use a known result, which is a p-series test. To prove the p-series test, you use the integral test. Okay, but you don't need it repeatedly using the integral test to prove it's convergent. And we also get an upper bound, right? Not only just proves it, we don't have a lower bound here from it. Right, so so take a look at this one. When I look at this, I can tell you immediately this is convergent. How do I know it? Can I estimate it even? The reason is natural log compared to n. Natural log compared to n is much, much smaller than any epsilon positive, okay? When n is large. So that means you can replace n by n square n. If you square n, then square of n divided by n squared will be 1 over n to the 3 over 2. 3 over 2 is positive. N is greater than 1. So that's why it's convergent. I'll get to some kind of question is how do you give a solid, give you an argument. Okay. So all the terms will be positive here. Right? All the terms positive. And I know natural log of n is less than equal to any positive, so less than equal to square n. You can figure it out for some larger n, okay? No, maybe, we don't know. You can pick up any number, right? Any larger number, let's say 10, for example. That's enough, yeah. So you can use that to prove this series convergent because the numerator can replace by square n. Okay. But today I'm going to continue to use the integral test to do that because it requires more mathematics to figure out for what n this inequality holds. Right. So this function, natural log of n squared equal to f of m, and f of x is going to be natural log of x over x squared. I hope I can evaluate this integral. Otherwise, I'm not able to use the integral test. Okay. All right. Also, I have to check whether this positive is clear, right? So if the most important thing is we have to check whether it's whether this integrable, you can evaluate integral. Okay. So first, this function is positive for x greater than equal to 2. Second, is it obvious decreasing? Not obvious. It's not obvious. Okay. So to verify this is decreasing, you have to find the derivative. When you find the derivative, this is 1 over x and x squared minus 2x, natural of x. I want to make sure this is less than, let's simplify first. This will be x minus 2x natural x. You take x out, you cancel it. Right. So under what condition this will be negative? So this negative if only if natural log of x greater than 1/2. But for what x this will be greater than or equal 1/2? Okay. Well, at least this one greater than or equal to e, greater than or equal to 3. I'm not sure it's 2, but it's 3 definitely guaranteed because 3 is greater than or equal to e. X greater than e, natural log x is greater than natural log of e, then which is 1, 1 is greater than 1/2, right? I don't need any calculator to figure it out. All right. So when x is greater than or equal to 3, this is negative. So at least this is decreasing on the interval from 3 to infinity. All right, great. So now you can apply the integral test. But you have to, the third one, you have to evaluate this integral. If I'm not able to evaluate this integral, then I have to give up the integral test. Of course, you can apply the comparison test to show this integral is convergent. Okay. How do I evaluate this integral? This is going to be x to the negative 2 natural x dx. I think I'm going to use the integral by integration by part. Okay, so I want to differentiate this x to the negative 1, right? Okay, this is my u, and then it switches order, right? This will be negative x to negative natural x, minus positive, and this will be x negative 1 and x. Okay, and the antiderivative will be this. So you can find the antiderivative. Great. Then you evaluate this. All right. So it's going to be the difference. It takes the limit, right? When b approaching infinity, integral from 2 to b. So you have to, let's see, put a negative. Natural log of b plus 1 over b, okay? Plus 2 natural 2 plus 1, okay? Yeah, because this is going to be negative x, natural log x plus 1, right? Now, clearly this limit is, this side's limit is going to be 0, so the answer will be natural log of 2 plus 1 over 2, okay? Okay, this is a finite number. Okay. You can use the Lupitas rule to prove the limit is 0, the first term. Okay. Now, what do you get? Well, we get when n equals 2, natural log of n over n squared minus the first term, which is 2 squared natural log of 2, is less than equal to this integral is less than equal to this, right? But this one we already find out the value even. And then finally, I'm more interested in the upper bound. Less than natural log of 2 over 4, right? Yeah, moved. Plus this. And then the other side, use the integral on the right-hand side, which is natural. So, it's magic. We can estimate the value, not only prove it's convergent. All right. Now, in case you are not able to evaluate the integral, how to check the convergence in another way? Okay. How to check the convergence of this integral from 2 to infinity, natural log of x, x squared. Okay. Well, to convert to this one, you can use you can use a comparison test. Okay. You have to figure it out. I just said that you have to figure it out for what value. The convergence so the convergence, remember we have the following theorem. Recall call that, right? If for fx is greater than or equal to 0, less than g of x, right? Okay, then we have from a to infinity f of x dx less than, okay? This is on the interval from a to infinity. So that means if the one on the right hand side is finite, then the one on the left hand is finite. So I guess the above one is going to be convergent, but you have to figure out the natural log of x. I just said that you still have to say this natural log of x is x less than x to the 1/2. Okay, so you have to claim that for x greater than some number. Now, how do you figure out that number? Well, if you're not sure, just put a larger number there. Okay, when x is sufficient large, definitely this is true. Okay, yeah. Yeah, so you can say x greater than 100, then guarantee it. You can use calculator, check natural log of 100 is less than or equal to 100, square root of 100. Okay. Another way, let's see, how can I quickly, yeah, this might be true. Okay, so you can take, yeah, let me show you how to put it, and I claim this is true. Okay, so I take the difference. Okay, I can yeah, take the difference. Okay, first of all, I look at the value. It's natural 9 minus 9 to the 1/2. So it's natural 9 minus 3. Now, why is this a negative? Natural log of 9 is less than 9 is less than e cubed. Okay, why the 9 is less than e cubed? E cubed is 2.7 something, right? When you cube it, okay, this is a number is larger than 9. So it's less than e cubed minus 3. So e cubed is 3. So it's going to be negative. Okay. Then you also look at the derivative, and as long as the function is the derivative is negative, then it's decreasing function. So it's 1 of x minus square x, right? Right? Yeah, half of square x, right? So you combine them. You combine this, right? It's a square x minus 1. And clearly, hold on. It's wrong. I'm going to, yeah. Let's combine them. It says x, that'll be correct. Okay. So clearly this is going to be less than 0 if x is greater than or equal to 9. Okay. Because x greater than 9 is the second term is greater than or equal to 3. So that's why f of h of x is always less than this. Okay, for x greater than or equal to 9, which is less than or equal to 0. So therefore, you always have this. And in other words, that is a difference, right? So it's guaranteed natural log of x is less than or equal to square x for x greater than or equal to 9. Okay. then nature of x over x squared is less than or equal to square x, and which is going to be x to the 3 over 2. Then you can use a P series. Okay. Then the integral from 9 to infinity is less than or equal to the integral from 9 to infinity. This is a finite, right? Because P is greater than 3 over 2. Okay. So that's the integral from 9 to infinity. This also implies the integral from 2, this is a convergent. Okay. Okay, so there are many using comparison here because you do need to replace natural log of x by square of x. Okay. All right. Let's recall this. Right, we know this is convergent, right? And I'm trying to recall what we did here. This is P is a 2, okay? So the integral, yeah, so I'm very interested in this again. Minus 1 less than 1 to infinity, 1 over x squared dx less than or equal to this. Okay, and I think this is going to be 1. Do you agree? Yeah, x to negative 1. Yeah, that's going to be 1. So in other words, this is less than or equal to greater than or equal to 1. Now, there is a famous mathematician called Euler. He found out this is just equal to pi squared over 6. Okay, which is of course is between 1 and 2. So then he said, well, you can use, then you go, how did you get this, right? So the limit is given pi squared over 6. Yeah, it's harder to tell, what time it is, right? If you check the when he lived, when did he live? Oh, it's a long time ago, 700, 300 years ago. Okay, how did he figure out this? He must use some other methods. Okay, there is another famous mathematician. Maybe there are very few people in the world that can be talked to the God. They know this kind of relationship. Okay, among the numbers, Ramanujan. Yeah, it's an Indian mathematician. Okay, I forgot the name of the movie. It's a very interesting movie. Yeah, if you have time to watch it, yeah, you should look at. Yeah, watch it. This movie. I just did it. Okay, he grew up in a very poor family, and much poorer than anybody here in this classroom. Okay, and he became one of the best mathematicians in the human history. Okay. But he can see many identities. Okay, he can write down so many infinite series, and the sum is going to be some number. Okay, it's really magic. He said he can, when he closes eyes, he can see it. Okay, but Euler gave us those two identity. As this is 90 over 90. I do not know how he did get it. Okay, we're not able to figure it out here. But this can be verified using computers. How do you do that? You take a difference. You can use a super fast computer to add the first 1 billion terms, and then you take the difference in the pi or pi to the fourth power over 90. Pi also you can write down many digits after the first, and after the digit point, right? But you can take the difference. They're almost the same. Okay, so you can verify this using computers. But anyway, those are the important. We know they're convergent, but actually the Euler can get the exact value of the limit. Okay. All right. So let's take a look at the next problem. And this is, yeah, some we can do this one. Okay, no problem. Okay, we look at this series. Okay, we want to check whether this is convergent. If it's convergent, can we estimate the value? We cannot get exact value. We're not Euler, okay? Maybe Euler even cannot. He's just lucky for those special series. He can write down the number, exact value. But this one, we don't know the exact value, but we can tell whether this series is convergent to some limit, to some number, and that number I can estimate, okay? So the best way to do is to use we're going to use the integral test, okay? So the corresponding function is going to be x over x to the fourth power. First of all, I have to think about whether I'm going to evaluate the integral, because if I cannot evaluate the integral, I shouldn't use the integral test. Why? Because if I verify this function is decreasing, then it takes so much time, right? Then I realize this cannot be evaluated, the integral, then what's the point? It just wastes of time. So you have to, at the very beginning, you have to use other methods to prove this series divergent or convergent. Okay, so take a look at this, right? I think this integral, the corresponding integral, will be convergent. Oh, yeah, the movie name is A Man Who Knows Infinity. Yeah, I think it's time for you to watch because Ramanuja, yeah, he's expert. Okay, nobody can beat him about this infinite series. Okay, in this world, but he passed away too early. Unfortunately, he's yeah he these early days, when you have some trouble with the lung and some, you're not able to survive. Yeah, it's not like this. Even right now, some disease we cannot survive, even coronavirus, if bad luck, Yeah, so this is what happened to him. He just coughed and cannot be recovered. All right. I think he learned the basic mathematics from 2 college students because his family owned a house. It's not good, nearby the university, and they rented it to 2 college students. So he just talked to them. Those are 2 engineering students, I guess. So he learned the mathematics from them. Yeah, he was born. He couldn't go to college yet, definitely. So that's why he got interested in mathematics, and he learned more than that's what he learned. Okay, that's an interesting story here. All right. All right, so this is f of x equals x over x. All right, let's see. First of all, this is going to be positive, for x greater than or equal 1, right? This is a positive function. Second, I have to verify this is decreasing. In order to verify this decreasing, I'm not sure it's decreasing over the whole interval from 1 to infinity, maybe from some large number. So I have to differentiate this function. And then I got here 1, x to the fourth plus 1 minus x, and the derivative here is 4x cubed. Okay. So I get 1 plus x to the fourth minus 4x cubed. Okay. Finally, I get, this is fourth power. Yeah, x to the fourth power And I think it's definitely it's negative for x greater than or equal to 1, right? Because the second term is minus 3x to fourth power. So actually it's less than, much less. You know, this is a negative. That's all enough. So if it's negative, then this is a decreasing function over the interval from there. Then you can apply the integral test. Okay, so but we have to evaluate this integral. You know, if I cannot evaluate this, can I show this is finite? Right, this is I think we can evaluate because right, we can let's try to find the antiderivative. Okay, so this question, yeah, question. Okay, let's find the antiderivative first, and then I come back to this. All right, substitution. Let u to be x squared. Du equals 2x dx. Okay, so then this u square, x times x is half of du. Oh, great. So I know this is going to be arctangent to u, right? Plus constant. And the u is x squared. Okay. So now I can evaluate this integral. Okay. And this is a half of b, right? Minus half of net arctangent to 1. Okay. So evaluate at the 2 endpoints and take a limit, right? And the first one, let's take 1/2 half of. This first one is a pi over 2, and that is b squared. Yeah, 1 squared. So still it's pi over 2. Okay, minus pi over 4. So it's going to be pi over 4, then divided by 2, pi over 8. So that is a value. We can get exact value. That's great. You know, sometimes you have to use a comparison test for integrals to prove it's convergent. Okay, then you can conclude that not only convergent, you can also minus the first term, okay, 1 over 1/2. You can also estimate. Okay, so it's between the value of this from here. You can say that the value of this infinite series is less than or equal to 1/2 plus pi over 4 and pi over 4. So the gap between them is only 1/2. It's pretty good. Okay, so it's not only finite, you can also estimate. Okay, so almost all the series here has a corresponding function. You can evaluate the integral. Okay, and if you cannot, then we have to learn more new methods to prove it's convergent or divergent. Okay, so our next problem. Let's try this one. Okay, I think that this is a clearly convergent. The question is how do you prove that? Because look at this. This is n, e to the n square. So the denominator increases pretty fast. Right, so the nth term decrease very fast. So you're not going to have an infinite sum. Yeah, you know the value, right? The limit will be finite. Okay, the limit will be finite. All right, how do you do that, right? Why is pi over 4 not pi over 2? That's right. That's my mistake. Okay, I copied it. Right? Just copied. All right. So look at this, right? We can use as a method to prove later on. We can learn more methods to prove it's convergent. But the integral test takes a little bit more time to prove it's convergent. But you can also get very good estimate, as I just told you. Okay, if you're able to use the integral test, meanwhile, you can also get an estimate. That's the advantage of using integral test. Okay, so my n is going to be n e to the n squared. That's equal to f of n. So I have to write down the function. What is x e to the negative x squared? Okay. So clearly this function is positive, so don't worry about that. Second, I have to prove this is decreasing. So if you just look at this quotient, the numerator increases, denominator also increases. Just because the denominator increases much faster, right? So so relatively, this rise of quotient decreases, okay? Just because the one in the denominator increases faster than the one in the numerator, so the ratio will be decreases. Okay. But that's just a rough idea. So we have to prove that. So the derivative of this function, okay? Use a product, right? Use a product. 1 times e to the negative x plus x times e to the negative x and negative 2x, right? So you will get minus 2x squared e to the negative x squared. So I get 1 minus 2x squared e to the negative squared. And clearly this is negative for x squared than equal 1, right? Yeah, because the second term is minus 2x squared. If x is squared is larger than 1, it's minus, right? So it's negative. So therefore, this is decreasing on the interval from 1 to infinity. Okay. The next step is to check whether this is a convergent. Okay, and what is the value if it's convergent? And we're lucky, we can evaluate this integral. Okay, I would do that directly, This is improper integral. You have to use a limit, right? But we can always use substitution directly, right? So let u to be x squared or negative x squared. I just use x squared, okay? du equals 2x dx, okay? So the integral, it's increasing, right? When x equals 1 to 1, when x equals infinity, infinity squared infinity. Okay, so x times dx is half of du. Okay, so the antiderivative of this function is this, and evaluate at the 2 endpoints. And then the first term will be 0, the second term will be just 1/2 e to the negative 1. Okay. Right? Great, so that is a value. All right, so now it's a finite, it's convergent. So our series is convergent. So what is that series? Oh, that series is going to be right from 1. That's n e to the negative n square minus the first term. The first term is just e to the negative 1. And then this integral, right? Integral is half of. And then, right? And this is the integral, right? In the middle. So this side is 1/2. The other side, look at this inequality, right? I think it's going to be 3/2e. So yeah, so this infinite series, right? This series is between these two numbers. Somewhere it's converging to some number between these two. Okay, so that's the integral. Right, finally, let's take a look at let's take a look at this this series. Okay. I want to see whether this is a convergent or divergent. Okay. Here, I assume that P is positive. Okay. When P is negative or 0, this is clearly is a divergent. Okay, so if P is greater than 0, if P is less than 0, what do you get? This is an n, natural log of n, right? So you can move it up negative p, and now negative p is greater, this is going to be positive. Okay, so clearly it's positive. This will be natural log of n and to the power 0, right? Which is 1/n. Okay, so that is that's a lower bound. So if you look at the partial sum, so we are going to learn the comparison. Okay, so that means the partial sum is going to be greater than or equal to this partial sum. And we know this goes to infinity as k approaching infinity, right? Why? Because we already did that for using integral test. Okay, so this implies I'm going to put from 2. Okay, from 2. So this is y cannot be 1 because nature log of, well, in this case maybe it doesn't matter, but it's otherwise be like 0 in the denominator. This will be infinity. Okay. So that's why we assume right now, we assume that P is greater than 0. Okay. So our n is going to be n, right? So this will be the value of the function n. So what is my function? My function here is f of x equals x times natural x to the power p. All right. I think that clearly this is a positive for x greater than or equal to, right? Second, this is decreasing. It's very clear because the denominator is increasing. Natural x to the positive power is increasing, x is increasing. So all I needed to do is to check to check whether I can evaluate the integral, and right. So consider this indefinite integral first. Right. Now, if you want to do the same time, you can put, yeah, you can do the direct. Yeah, let's look at the direct. Okay. Then you use a substitution. Okay. You let u to be natural log of x. And then du equals 1 of x dx, right? Okay, so the above integral becomes, when x equals 2, I get natural log of 2. When x is infinity, natural log of infinity is still infinity. And that's u and du, okay? So the entire derivative of this function, this is a u to the negative p, right? So the entire derivative will be 1 minus p u to 1 minus p. Evaluate these two endpoints. Because p is then it's up to p, the value p. If p is greater than 1 or p less than 1, right? This is when p is not going to be, yeah, this is assuming p is not going to be 1. Otherwise, it's not going to be u to 1 minus p, okay? So clearly, you will get, when p is greater than 1, this is going to be finite. And this will be, this will be 1 minus, negative 1 minus 1. If p is greater than 1, okay? Because it's like a 0 minus, right? This will be infinity if p is less than or greater than 0. And similarly, you can also show that when p equals 1, and the only difference is the integral, it will be natural logarithm, right? That's the infinity, okay? Anyway, so the only non-trivial case is when p greater than 1. And that's it. So this integral from n from 2 and n natural log of n to the power p minus the first term, 2 natural log of 2 to the power p, is less than of this integral, right? Yeah, it's less than or equal to. So you can tell when it's convergent, when it's divergent. Okay, so in the case, if p is greater than 1, right, less than infinity, then I can tell that greater than the value. What is the value here? We get p minus 1. I think p minus 1. And this will be natural log of p, p minus 1, okay? And this other side, p minus 1, plus a term from, plus the first term. Sorry, to the power p. So you can even estimate. Yeah, you can even estimate this too. Okay, it's between this, right? Because this is this can be evaluated. Well, So as I showed you in some cases, the integral test is very powerful. You can not only prove it's convergent, you can also get an estimate on the value. Okay. Okay. So that is today's class, and